is BMS Connections, written by me, Jean Leguay.
Here's the legal stuff. So in a previous video I spoke to you about points. These are the signals that go in and out of a controller, a PLC, or a BMS if you want to call it that. So we have digital inputs and digital outputs. Digitals are on-off signals. They have two states. So digital inputs are typically switches. Digital outputs are typically to contactors and relays. Then we have analog inputs and analog outputs. Analog signals are continuous signals. Voltages, 0 to 10 volts normally in BMS. So we have the analog inputs coming from sensors such as humidity sensors, airflow sensors, pressure sensors, and the analog outputs going to valves and actuators. You also have a special type of digital input, which is the pulsed input. We get this from electricity meters, and basically every time the little disc goes round it gives a pulse. We don't care about the on-off status so much. What we do instead is we count the pulses. What's extremely important is that our computer runs fast enough so that it doesn't miss any pulses. Let's talk about how signals come in and out of a computer. I'm going to talk about an analog signal, and this analog signal is coming from something in the real world. It's coming into the computer. The computer's doing something in there, making some decisions, and then it's controlling something. So perhaps this is a temperature, and maybe we're outputting to, let's say, a chill water valve. Let's go through this in detail. We have the analog part of the system, which is the real world part of the signal system. In the real world, all the signals exist as real values, 0 to 10 volts normally, and things are really happening. In the real world, everything is measured in engineering units. That'll be degrees C's, watts, pascals, that sort of thing. They're engineering units. Then we have the digital part of the system. This is the stuff that's inside the controller. Everything in the digital part of the system is actually stored in ones and zeros. So we have to convert the analog into ones and zeros. And the computer makes decisions based on the ones and zeros, basically. Let's look at this in detail. Firstly, we have the physical world. This is where things are really happening. Maybe we have temperatures that we're measuring, pressures that we're measuring. So this is the real world where things are really happening. Things, once again, are measured in engineering units. We sense the real world with sensors, temperature sensors, pressure sensors. So we sense the real world. We have something which changes because of something changing in the real world. And then we measure that change. We condition that change into a signal. Now, in air conditioning, this signal is invariably 0 to 10 volts. So we take that signal and we change it into 0 to 10 volts. If it's a temperature, it's actually a resistance, but still, it still is actually 0 to 10 volts when you think about it. So we condition into a signal 0 to 10 volts, and we feed that signal to our controller. Now, our controller talks in digital. Our BMS talks in digital, so in order for the signal to go into the BMS, we need to convert from the analog 0 to 10 volts into digital ones and zeros. And for that, we use an analog to digital converter, an ADC. Based on that converted signal, the controller makes some sort of decision. It's controller after all, so it needs to control. And then it needs to output the result of that decision. But that result is still digital. We need to convert it into analog so that it can go out to the real world. To convert it into analog, we use a digital to analog converter, a DAC. Then we output, from the DAC, we output a voltage, 0 to 10 volts. And that voltage goes to an actuator, a valve, or a VSD, or something which actually changes things in the real world. And that then changes the real world, and that's our complete loop. So let's talk about how these various things work. First thing I'm going to talk about is a DAC. Now, there is a clever little bit of electronics called an op-amp. That's short for operational amplifier. Sounds very grand. An op-amp is a Swiss Army knife of electronics. It can do any number of different jobs, depending on how you hang resistors and capacitors off the side of it. So I've got an op-amp. Oh, the symbol for an op-amp, by the way, is a triangle. That's an op-amp on the right-hand side. I've got an op-amp which I have configured to be a summator. It adds things together. See, that's a sum sign inside it. It adds things together. So if I give it different voltages on its little legs, it'll add all those different voltages together and give us an output. On the left-hand side, I have a whole series of different size voltages. Now, if you look at that, if you add all those together, it comes to roughly 5 volts. And each one of those voltages is being controlled by 1 bit of a digital word, so a digital value. As I change those digital values, the switches close and the voltage goes through, so the summator adds them. Let's give you an example. Here I've given it a digital word, 11100110. The switch is closed, and what's gone through has been 5 plus 2.5 plus 1.25 plus 0.1563 plus 0.0781, and all of those add together to make 8.8594 volts. So that's how we take a digital value and we change it into a voltage. Making an ADC, an analog to digital converter, is a little bit more complicated. So I'm going to go through that. Now, the first thing, this is an ADC circuit simplified. Now, the first thing to notice is that this bit here is a DAC. So that's a DAC. Now, the digital word in this case is going to be a digital counter. We're going to come to what that does. I've used another op-amp as another triangle there on the right hand side. It's got stop counter written on it. This time the op-amp has been configured to be a comparator. It's going to compare the two signals, and when the two signals are the same, the two voltages coming into the little legs on the left, when those two voltages are the same, it will trigger a stop counter signal. Okay, let's go through this how it works. I've connected up my ADC to a tank level. And this tank at the moment is at 25%. So 0 to 10 volts, 25%, it's outputting 2.5 volts. My ADC, which has got a DAC attached to it, the DAC part of it has got 0 in the counter. So 0 in, 0 volts coming out of it. So the comparator, the stop counter one, is saying, well, they're different. So what I'm going to do is I'm going to start the counter on the DAC. And I put a 1 in there and it outputs a voltage. Still not the same. I put 2 in there, which is 10 in digital, and it outputs a voltage. Still not the same. So I put 3 in there and it outputs a voltage. Still not the same. It's going to take a while. So I put 4 in there, which is 100 in digital. Outputs a voltage. Still not the same. Getting bored. Output 5 in there, outputs a voltage, still not the same. 6, Outputs voltage, still not the same. We're going to fast forward. Thank goodness we fast forward. So I've put a much bigger digital value in there because the counter's counting up, and now it's outputting a voltage 2.422 volts. Okay. Step another one, 2.4611 volts. Still not the same. Oh, bang! It's now, the DAC is now outputting 2.5 volts. The level sensor is outputting 2.5 volts. And the comparator lights up to say, that's it, you've got it, stop the counter. Now, whatever you've got there in the counter is the digital equivalent of 2.5 volts. Because a DAC produced 2.5 volts when you gave it to it. So that's it. That's how an ADC converter converts. It takes a while because you have to start the counter each time and it has to count up and then grab it. Bang, got it. So depending on the value, it could take a little while. Now counters are quite fast nowadays, but it still takes a time. In addition to that, hardware manufacturers are cheapskates. ADC converters are quite big chunks of electronics. So what they do is they actually only install one of them. You might have 8 analog inputs, but there's only one analog to digital converter. And what they use is a thing called a multiplexer. Now a multiplexer is a telephone exchange. What it does is connects up to the first analog input and reads the value. Starts the counter, got it, passes it through. Then connects to the next one. Starts the counter, got it, passes it through. Then connects up to the next one. Got it, passes it through. And it carries on doing this till it gets to number 8, and then it comes back to number 1. Now, what you have to appreciate with this is it might be anything up to a few seconds before it gets back to analog input number 1. So there is an appreciative time interval. So what we say is analog inputs don't read continuously. In fact, what they do is they sample. Every now and then, the computer basically, maybe once every 2 seconds, looks at analog input 1. And then once every 2 seconds, looks at analog input 2. There's a lot of readings which are missed out. Let's have a look at some of the consequences of this sampling and what can go wrong and how we can fix it. Here's a temperature in a room. This room is controlling around about 22 degrees. Temperature's going up and down a little bit. Now, that's fine, except for when we ran the cable, we ran it past a fluoro. And that fluoro just happens to be flickering today. So we're getting some spurious readings. And those spurious readings are through looking like that. Now, what's happening is that when it flickers, the temperature's either going to 0 degrees or it's going up to something ridiculous. Now, that could cause a problem if we read that in, because the control system might take it as a real reading. Now, first thing to do is remember that the ADC will only sample periodically. So the ADC sampled input, what the BMS system sees is actually this. Sod's law says that even though the flickering is only happening occasionally, we will occasionally sample it. So that's going to give us a bit of a problem because the BMS system is seeing the temperature suddenly leaping down to 10 degrees Celsius and then suddenly not long afterwards leaping up to 80 degrees Celsius. Well, it's going to try and control to that, and that's going to maybe cause problems because the whole system will go into oscillation and it's just going to not be good. So how can we fix that? We use a value which we call the alpha. The alpha is a filtering value. It's a percentage filtering value. And basically, alpha of 100 means just take the raw readings. As you reduce alpha, we take less and, well, we filter it, we smooth out the signal. So that, let's show this again. This is with alpha of 100, so that's no filtering. This is with alpha of 10, and you can see how much the signal has smoothed out. We've still got a few rogues in there, but it's nowhere near as bad. In fact, it looks pretty good. This is with alpha of 5, and it looks pretty well like a straight line. We're not picking up any bad things. And that's really what is happening in that room. The temperature's fairly even, despite the flickering fluoro. So we went from this totally unstable looking system to this stable looking signal. And this is something we can control with. Here's another signal. Now this isn't being caused by a fluoro. This is a static air pressure on an air handling unit. Now static air pressure is always unstable, and depending on where you put the static air pressure sensor, it would be more or less unstable. You should try and mount the sensor as far away from the fan as you possibly can, but without getting near to any bends or curves or anything else in the ducting. It's often very difficult to find a good location, and more often than not we have very, very unstable signals like this. We can't control to a signal like that. The control just will be rubbish. It will be constantly hunting. So we need to filter it. Firstly, let's have a look. The ADC samples it, and with an alpha of 100, it looks like that. That's still not good. The BMS cannot control with that sort of a signal. It'll be trying to correct what's not really there. So we use the alpha. We reduce the alpha, reducing the alpha to 50. We've got a much more controllable signal now. Reducing the alpha to 5. Now that is a signal we can control to. It's not, you might say, well, it's actually lying. Yes, it is actually lying. But then we're sampling anyway. We're not taking continuous values, we're actually sampling. And sampling is part of statistics, and statistics is all about lying. So that's okay. So we went from an unstable thing like that to a controllable signal like that by using alpha. Now, ADCs and DACs, they're expensive pieces of kit. The higher the bit rate, the more expensive they are. The other place you would have heard about ADCs and DACs is in MP3 players. MP3 players also take digital signals, which are the music, and convert them into analog signals, which is the music that you actually listen to. In air conditioning, typically the ADCs are 12 or 14-bit resolution, which means that you wouldn't really notice the steppiness, and they're not fabulously expensive. Now, pulse width modulation. This is where we take a digital output and we turn it into an analog output. And the way we do that is by switching it on and off for a period of time. And let's say that our entire period of time is 1 second. If I switch it on for a quarter of a second, let's say it's a heater. Let's say I've got a heater, and every 1 second I switch the heater on for a quarter of a second. What's going to happen is the heater will only heat up to a quarter of its maximum heat. If I turn that heater on half a second every 1 second, 50%, the heater will heat up to half its normal value. So a 300 kilowatt heater will output 150 kilowatt. This is how we control heaters, such as electric duct heaters, so that something which is normally and traditionally on-off can be controlled to a percentage. And because the heater is quite a large chunk of metal, you're not aware of the flickering, because it evens out. So we use this to control electric duct heaters. When we talk about digital outputs, there are two types of digital outputs. There's the relay type, which we call the volts-free contact. It's called that because there's no actual volts on it. All it is a switch. It just supplies a relay closure. It doesn't supply volts. If you want volts, you've got to put volts onto it. The second type of output is the triac output. This uses transistors to output. Now, typically, this outputs a voltage, 24 volts typically. The triac is a high impedance device. It has unlimited operations, as opposed to the relay, which will work 500,000 times and then fail. And they are very accurate. They will run 500,002 times and fail. The triac, unlimited operations. The only downside of the triac is that the potential remains after the gate is switched off. What this means is, if you turn a triac on, you'll see it come on. You can measure it with your voltmeter and see that it's on. If you turn it off, when you measure it with the voltmeter, it still looks like it's on, because the voltage needs to go somewhere. If we use a digital output to control, let's say, an electric duct heater, if we're outputting to a contactor and we're switching it on and off twice a second, that contactor is going to be stuffed pretty quickly. So that's not going to work. So what we use instead is a solid state relay, which is a big transistor. Essentially, it's a solid state contactor. Okay, now this once again is a high impedance device, so you have to have a resistor so that there's a way for the voltage to drain away. Now the problem with a solid state relay, unlike a relay, relays almost always fail open. A solid state relay will fail closed as often as it fails open. And that can be a bad thing. You don't want a heater which is permanently on. Because if the heater is permanently on, let's say the airflow stops, then the heater overheats, and then you have a fire. So for safety reasons, we have to wire them up like this. You have an isolator on the load circuit, and then you have two thermal overloads. These are fire thermal overloads, so that in the event of a fire, the power is cut off. We've also got a resistor in there to allow the potential to drop away so that it will drain, because remember, it's a high impedance device. Now, problem with digital outputs to things like contactors and solenoids. Contactors and solenoids are effectively magnets and big coils. And what happens is we turn the power on to the big coil, that becomes an electromagnet, and then it draws the magnet or the core towards itself. And that opens up the contactor or the solenoid or whatever. That's great. The problem then comes up when we switch the power off. When we switch the power off, the electromagnet, the coil ceases to be an electromagnet, and the big magnet, which is the core of the contactor, moves. Now we have another situation where we have a large magnet moving very fast past a coil. that is a generator, and that generates voltage, and the voltage it generates is proportional to the speed at which it's moving, and it's moving very fast. So it generates a high voltage in the thousands of volts, and that high voltage comes belting back down the DO's circuitry and goes straight into your PLC, where it blows up bits of the circuit board. That's not a good thing. There's two ways we can deal with this. The first way is by putting a diode across the output circuit, and that's that little circuit I've written there, and that's called a freewheeling diode. What that does is it allows that voltage spike to be drained away. Another method, the preferred method, is using an interposing relay, which is a relay which sits in between your contactor and the controller. Now in Australia, we are encouraged to use interposing relays, specifically because we have to maintain segregation. This is an extract from AS3000, and it says basically there is low voltage and there is extra low voltage, and never the twain shall meet, they shall be separated. So this is how the system should be set up. You've got the BMS living in the extra low voltage area, and so everything in there is 24 volts, nothing really much higher than that. And then you've got contactors and solenoids and that sort of junk living in the low voltage area, 240 volts, anything up to 1000. And in between you have the interposing relay, and that bridges from extra low voltage to low voltage. It is another thing to go wrong, so that is a problem. However, when the contactor opens and closes, it sends a 2000 volt spike down the line. It's the only thing that's going to get blown up is a $15 relay, rather than a $3,000 BMS system. So it's another thing to go wrong, but it's effectively a fuse. So all up, this is how your cabinet should be arranged. There should be an extra low voltage area with its own extra low voltage trunking where the extra low voltage cables come down. There should not be any 240 volts in any of that area. In between the extra low voltage and the low voltage in the blue, you have the interposing relays. They're the grey squares on the right. If the system uses a transformer, that transformer should be outside of the extra low voltage area. Now let's talk about some inputs and outputs and syncing and sourcing. Syncing means that the signal goes away, it syncs, it goes to a 0 volt, an earth or a return. Sourcing means that the screw that you physically connect to is the source of the voltage. It's where the voltage comes from. So, here we have inputs and outputs arranged in what I call the sensible arrangement. The inputs are syncing. Basically, there's 24 volts, goes out to a switch, and when that switch closes, 24 volts is presented to the input screw. That then syncs because the input screw is connected to the common or 0 volts, and that syncs the input. Now the outputs are sourcing outputs. The screw on the BMS is the source of the 24 volts. So with this system, these are volts-free contacts. With this system, when the output closes, when the relay contact closes, output 0, for instance, becomes 24 volts. That 24 volts travels to the load. The other side of the load is connected to the return, so the load switches on. When you're fault finding this, you'll find that 0 volts is off and 24 volts is on. contrasting that with the American system. In the American system, the inputs are sourcing and the outputs are sinking. What this means is 0 volts goes to a switch. The screw on the BMS, input 0, is at 24 volts, is connected to the 24 volts. When the switch closes, we supply a return path. So we're switching the return. And when the switch closes, the input comes on because the current can flow because we now have a complete path. The outputs are sinking outputs. In other words, the screw on the BMS is connected to 0 volts. The load is permanently powered up. So the load permanently has 24 volts on it. But of course it doesn't come on until we switch the return. So with the sinking output, when the contact closes, output 0 screw then becomes 0 volts and the load comes on. Now I find this system to be very, very, well, fraught with danger. With this system, 24 volts, if you're measuring it on the screw, 24 volts is off and 0 volts is on. Luckily, I don't think there's many BMS systems still using this system. So let's look at some wiring, how we connect up different things to our BMS. Firstly, a digital input. This is a switch. This is how we connect a switch to the BMS. We simply have two contacts which we can connect to the plus and minus inputs of the BMS on the digital input. Here's how we connect up a thermistor, an analog input thermistor. Now a thermistor is essentially a resistance device, so it's not actually polarity sensitive. Doesn't matter which way round you connect it. With a thermistor, we have to correct it. They're never completely correct. They always need a little bit of calibration. So when we calibrate the thermistor, what we do is we change the offset. To do this, you open up the program, double click on the input block, and this is the same for all systems, whether it's an Initech or a Schneider or whatever. You double click on the input block, you find the thing that's called offset. Now this is the Initech I'm showing you here. You find the thing that's called offset and you change it. And what you do is you take what you're actually reading using your digitally accurate meter, what it's saying on the screen, in other words the display value, you take the display away from the actual and that's what you put into the offset. And when you do an OK on this, the actual and the display should be the same thing. Here's an analog input where we're taking a voltage in. Okay, so this is a 3-wire system. This is the sort of system you'll find on percentage RH, pressure, flow, level, that sort of thing. Typically it's outputting 0 to 10 volts. So firstly we have to give the thing power. So we give it 24 volts from a power supply unit. Then we have to connect the output of the sensor to the input of the BMS. And we connect that just to the plus side. So just one connection to the BMS on the plus. The 0 is typically, so the minus side, sorry, is typically already connected to 0. So that's all good. The issue you'll have with this sort of system is that you need to convert it from 0 to 10 volts into engineering units like percentage RH or pressure or flow or whatever, because within the program we need to see this in engineering units. So we use a universal curve. That's what it's called in the Initech. Other programs, they'll call it different things, but essentially it's just a converter that allows you to convert an input into an output. It's a scalar. So first, it's 0 to 10 volts, so we make the input 0 to 10. Now, how to calculate the output? What we do is we measure it. So we use our handheld RH meter or pressure meter or whatever to measure the value. And then we look on the screen to see what the voltage is that's currently coming into the system. Now, normally these things are pre-calibrated so that what's supposed to happen is 0 to 10 volts is supposed to correspond to, let's say, 0 to 100% RH. And that's great, except for there are voltage drops. So it's never perfectly accurate. We need to make a very slight change. So what we do is we measure the value and we look to see what voltage there is. We divide the value by the voltage, multiply by 10, and that's what we shove into that box. I better run through an example. Let's say, for example, I'm measuring RH, and I measure it and it says it's 43.2%. And then I look on the screen and the screen says currently there's 4.09 volts coming in. Okay, so I do the calculation, 43.2 divided by 4.09 multiplied by 10 is 105.62. And I shove that into that box, and now it's going to give me the correct engineering units. This is a thyristor digital output. Typically we're going out to relays, solenoid, solid state relays. Remembering we're going through an interposing relay. Solid state relay counts as an interposing relay. The system is outputting basically 0 to 24 volts. 0 or 24 volts. It's on or it's off. This is a digital output using volts-free contacts. Now remember, with volts-free contacts, the BMS is only supplying a contact closure. So we have to put power into the BMS from a power supply unit. The BMS closes a contact that goes off to the interposing relay, and then we have to complete the circuit by bringing the negative from the interposing relay back to the power supply. Analog outputs. This is to things like valves, actuators, VSDs, that sort of thing. Normally they need power to actually work, so we connect 24 volts to the power supply unit, and then the voltage signal comes out of the BMS and connects up. If it's something like a VSD, it normally has its own internal power, so the only thing you connect is the voltage signal from the BMS. Now, I better talk about power supplies while we're here. Typically, PLCs, especially the ones on BMS systems, come with 24 volts available on them. Now, don't use that 24 volts to try and control your valves. What will happen is you'll just burn out the little voltage regulator within the PLC. So you need to have a good external power supply. It needs to be a regulated external power supply which gives a lovely DC value, 24 volts. And then we need to earth. We need to make sure that everything is earthed so that everything is working off the same 0 volt reference. This is very important. If we don't have everything off of the same 0 volt reference, then what can happen is the BMS could output, say, 4 volts to a valve, and that valve might be a different 0 volt reference. It might be a 0 volt reference which is 2 volts higher than the BMS. In which case the valve sees the 4 volts as 2 volts relative to its 0 volts. So we need to have everything at the same 0 volt reference. So what I recommend you do is you have all of the neutrals earthed. If everything is down to earth, then everything is on the same 0 volt reference. And that's the end. Thank you for listening.